Alright, welcome to today's class. The topic is Euclidean algorithm and related topics. Let's take a definition of prime number. Prime number plays an important role in number theory. So a positive integer p is called prime if the only positive factors of p are 1 and p. Now, a positive integer that is greater than 1 is not prime, but is called composite. For example, 2, 3, 5, 7, 11, 13, 17 are all prime numbers, while 4, 6, 8, 9, 10, 12, 14, 15, etc. are called composite numbers. Let's take an important theorem here. This theorem is called the fundamental theorem of arithmetic. Every positive integer greater than 1 can be written uniquely as a prime or as a product of two or more primes where the prime factors are written in order of non-decreasing size. For example, 100 can be written as a product of two primes. 100 can be written as 2 raised to the power 2 times 5 raised to the power 2. 333 can be written as 3 raised to the power 2 times 37. While 64 can be written as 2 raised to the power 6. Divisibility property. Let a, b, and c be integers. Then, if a is divided by b and a is divided by c, then a will be divided by b plus c. Let's look at the theorem of mathematical induction, which I believe you're already familiar with. If Pn denotes a proposition that depends on n, that is step number 1, then step number 2 in proof using mathematical induction is that you're going to prove that P1 is true. And if P1 is true, you're also going to prove that Pn plus 1 is true whenever Pn is true. Then, if these three conditions hold, you now conclude that Pk is true for all k in n. Let's take an example. Prove by induction that 11 raised to the power n minus 8 raised to the power n is divisible by 3 for all n in the set of natural numbers. So any value you pick for n, you are going to discover that 11 raised to the power n minus 8 raised to the power n will be divisible by 3. Let's do the first step. For n equal to 1, you're going to see that you're going to have 11 minus 8, which is 3, and 3, of course, is divisible by 3. Therefore, 11 raised to the power n minus 8 raised to the power n can be written as a factor of 3. We want to prove it holds for n plus 1. That is 11 raised to the power n plus 1 minus 8 raised to the power n plus 1. We want to show that it's divisible also by 3. So if we can show that, then we conclude that 11 raised to the power n minus 8 raised to the power n is always divisible by 3, and that statement is true. Now, this is how we do it. By the time you express 11 raised to the power n plus 1 minus 8 raised to the power n plus 1, you're going to have 11 times 11 raised to the power n minus 8 times 8 raised to the power n. And by simple factorization, you're going to have that 3 is outside here, multiplying 11k plus 8 raised to the power n. So we have been able to show that whatever it is at n plus 1, we are definitely going to have a factor of 3. And this 3 here shows that this function, entire function here, can be divisible by 3. Hence, by induction, we conclude that the statement that n, 11 raised to the power n minus 8 raised to the power n is always divisible by 3. That is how to show that by induction. The next subtopic is the greatest common divisor. Now, by definition, let a and b be integers, and both of them must not be 0. The largest integer d such that d divides a and d divides b is called the greatest common divisor of a and b, and is denoted by GCD of a and b. Now, proposition. We are going to use the proposition to finding the GCD of two numbers. proposition. Let A and B be positive integers and let P1, P2 up to Pn be all primes that appear in prime factorization of A or B, so that A will be P1 raised to power A1 down to Pn raised to power An, and B will be represented as B1 raised to power B1 and up to Pn raised to power Bn. Then we are going to have that the GCD of A and B, the pair A and B will be equal to P1, the minimum of A1 B1, P2, the minimum of A2 B2, down to Pn, the minimum of An Bn. Now let's use that proposition to find look at some examples. We should find the GCD of the following pairs: 3 and 12, 1024 and 625, then 7 and 15. Solution. We can write 3 to be 1 times 3 and 12 to be 1 times 2 raised to power 2 times 3. Therefore, the GCD of 3 and 12 will be 2 raised to power the minimum of 0 and 2, then 3 raised to power the minimum of 1 and 1, and that will give us 2 raised to power 0 and 3 raised to power 1, and that is equal to 3. Hence, 3 and 12 are not coprime. Now, for them to be coprime, it means that the GCD will be 1. But since the GCD is 3, we say it's not a coprime. Other examples follow the same. So the GCD of 1024 and 625 is 1. So in this case, you say the two numbers are coprime. The two numbers you're looking for the GCD are coprime. Now the other example, which is for 7 and 15, the GCD is also 1, meaning that these two pairs, 7 and 15, are known as coprimes. The Euclidean algorithm. Now this Euclidean algorithm is a step-by-step algorithm on how to find the GCD of a pair of numbers. Now, given a pair AB, we may be computed by repeated application of the division algorithm, that is writing A, we write A to be equal to the quotient times the divisor plus the remainder. B, the same thing, the quotient times the divisor times the remainder. So every number can actually be expressed with that, using the quotient, the divisor, and the remainder. And once you do that, the GCD of a pair A and B is actually R times N, R being the remainder, times the number of iterations. Now this is a practical example. So if you use the Euclidean algorithm to find the GCD of 3, 4, 5, and 92. Now the solution, when you apply the Euclidean algorithm, this is what you're going to have. And if you follow it step by step, you're going to see that the GCD of 3, 4, 5, and 92 will be equal to 23. Now, there's a subtopic here known as integer linear combination. There's a theorem, so there exists x, y in the set of integers such that this pair can actually be expressed as integer linear combinations of ax plus by, where x and y are integers. Let's look at an example. Express the GCD of 3, 4, 5, and 92 as an integer linear combination of 3, 4, 5, and 92. Solution. By applying the Euclidean algorithm in concert with the division algorithm, starting with A equal to 345 and B equal to 92, we have seen this before. So we are going to have the GCD to be 23. But you're not going to stop there. It's a continuing. We are going to go in a reverse order now. So going from 23 backward, then you're going to find x and y. And from what we have done on the board, you're going to see that x will be equal to -1 and y will be equal to 4. So those numbers can actually be represented as integer linear combination using the GCD. Thank you.